Welcome to my pre-algebra class. We're going to be working on Chapter 6, Section 8, which is solving word problems either by making a table, an organized list, or make a model, and trying to identify patterns. The following video gives you a little more information on that.
How do you solve any math problem in just a few seconds? Hi, I'm Jimmy Chang. I've been teaching college mathematics for almost a decade, and we're here to talk about a few steps that will help you solve a math problem in just a few seconds. Now, can any and every math problem be solved in a few seconds? No, there's going to be problems that are going to be more involved than that, but there's also a lot of math problems that can be solved in just a few seconds. But the most important thing to really think about in order to do that is you need to have a lot of things already in your mind. You need to have a lot of formulas stored up there and be very familiar with them. And also, this is a really strong tip for you, be really strong with your multiplication tables. The more work you can do in your head, the better off you'll be. Not that you can't write stuff down, but once you have it in your mind, you can immediately write down what kind of information that you need after reading a particular problem. Now, once you have the problem written down or in your mind, you can easily solve it in your head. You can write out a couple of basic steps on paper, but basically, the more you know in your mind, the faster you can do a particular problem. So, I'm Jimmy Chang, and that's how you can solve a problem in just a few seconds.
Well, we'll see how many of these problems we can solve in a few seconds. We're on page 272, guided practice 1 to 6, exercises 1 to 12. So your paper is headed, folded in half, and you have your books open to 272.
How do you teach children discrete mathematics?
I think we have Jimmy Chang back again.
I'm Jimmy Chang. I've been teaching college math for nearly a decade, and we're here to talk about
Okay, he's gone. All right, the problem at the top of page 272 says use this problem for exercises 1 to 6 in the guided practice. The figure below shows a pattern of acute angles, angles less than 90 degrees, formed by 2, 3, and 5 rays with a common endpoint. In this pattern, how many acute angles are formed by 8 rays with a common endpoint? Well, the first one, we can see we get 1. 2 rays make 1 angle. And then if we put 1 in between, now we have 3 rays and 3 angles. If we put another one in, we have 4 rays and 6 angles. And then we have one more, as we're trying to establish a pattern here. This one has 5 rays, and we have 1, 2, 3, 4, 5, 6, 7, 8, and then 9 and 10 angles. So 2 rays, 1 angle. This one has 3 rays, 3 angles. This one has 4 rays, 6 angles. And this last one has 5 rays and 10 angles. You don't have to write this down. We're trying to figure out what's happening here and see if we can figure out a pattern. So question number 2 says, what is the question that has to be answered? And it is, how many angles are formed by 8 rays? And then question number 4, in the figure above, it shows 4 rays with a common endpoint. Name the 6 acute angles. So that would be the third example here, and we'll put the names in. It's A, the points in it, they had B, C, this was Z, and this was x. So the 4 angles, there are actually 6 angles, excuse me. You have this 3 small ones, angle AXB, angle AXC, angle, I'm not doing the small ones, I'm doing all those that start with 8. Let's do all the small ones first. I'll go back. All right, I have angle, the small angles, AXB, angle BXC, and angle CXZ. Then I have an angle AXC, these are the larger ones, and BXZ. And then finally I have the largest angle AXZ. And problem number 6, what is the solution to the problem? Well, on the opposite side of your paper, put number 5 here. Please be sure you put 5 here. Complete the table, and we'll see if we can get our answer. So the top of this table is the number of rays, and the bottom is the number of angles. So we're going to fill in the table and see if we can figure out the answer. So if there are 2 rays, I get 1. There are 3 rays, I get 3. If there are 4 of them, I got 6. If there were 5 of them, I have 10. So if I have 6 of them, there doesn't seem to be any real pattern here going from here to here, but there is something happening here. It's going up by 2, then by 3, then by 4. So the next one would have to be 15. And then 7 would have to go up by 6, which would be 21. And then the next one would have to go up by 7, which would give me 28. So my answer to number 6 is that there are 28 angles. And that moves us into the exercises, and we're on page 273 right now. Problem number 2, the figure below shows the number of line segments that can be drawn between 2 points, then between 3 points, then 4, and then 5. How many line segments can be drawn between 9 non-collinear points? Now, do we want to draw a 9-sided figure and see how many we can get? No, we want to try a pattern. So if I have 2 points, I get 1 line segment. If I have 3, I get 3. If I have 4, I get a total of 6 line segments. If I have 5, if you count all the line segments in that star-shaped figure, you're going to, on the outside you have 4, and then 5 and 6 from one vertex, 7 and 8 from another, and then 9 and 10. 1, 2, 3, 4, or 5 on the outside. So there's 10. Well, it looks like we got the same pattern going on over here. So we know when we reached 8, so when we had 7 there were 21, and when there was 8 we added 7 and we got 28. So if there are 9, we're going to add 8 and get 36. Having difficulty adding there. Okay, so the pattern's been used twice now. Number 4. Jennifer Nigg bought a bicycle helmet that cost $31.29. She gave the clerk two $20 bills, which totals $40. How much change did she receive? So if I take 2 times 20, which is the $40, and then subtract the $31.29, we get our answer. So subtracting 9 from 11 is 2, That's going to be 8. That'll be 6. What am I doing? That's 9, so that should be 7. It's a little early in the morning for me. And then 1 from 9 is 8, so it's going to be $8.71. I made enough mistakes in that one. That should make you feel good. Number 6. The figures below show all the diagonals can be drawn from one vertex of a quadrilateral, a pentagon, a hexagon, a heptagon. How many diagonals can be drawn from one vertex of a decagon? Well, from one vertex I get one diagonal. From 2, and that has 4 sides. Let's go back and change this. So from a 4-sided figure, I can get one diagonal from one vertex. From a 5-sided figure, I can get 2. From a 6-sided figure, I can get 3 diagonals from one vertex. And from a 7-sided figure, I can get 4. Let's see if we can figure out a pattern here. Well, 1 is 3 less, 2 is 3 less, 3 is just 3 less, and 4 is 3 less. So it must be 3 less than the number of sides is what you can get for the number of diagonals. So 3 less than the number of sides. So that's our pattern, and we're going to apply it for a decagon. A decagon has 10 sides. So if I take away 3, 10 minus 3 would give me 7 diagonals from one vertex. Problem number 8. Often you can use a geometric problem to model a real-life situation. For example, exercises 7 to 10 refer to the following problem. You have 8 people at a party, and each person shakes hands with each of the others exactly once. How many handshakes are exchanged? So they actually did, the dots represent the people. So we have 8 dots, and the red lines are the handshakes. So number 8, which geometry problem in this lesson seems most closely related to the handshake problems? Well, if we back up and look at number 2, that seems to be similar to this because it's finding all the line segments, which would be all the handshakes that could be drawn between any number of points or people. So number 2. And problem number 10. Describe how to solve the handshake problem using a strategy other than identifying pattern. Well, you could actually have people shake hands and count the number of handshakes. And problem number 12, write a problem that you could solve by identifying each pattern, then solve the problem. Well, number 12, it looks like they're adding blocks. So we could say how many blocks are in the stack with a base of 10 if you place one less than the previous row. Until you have one block on top. So first one I have 2 plus 1, and I got 3 blocks. The next one's 3 plus 2 plus 1, and I have 6 blocks. The next one is 4 plus 3 plus 2 plus 1, and I have a total of 10 blocks. And the next one is 5. And that's 5 plus 4 plus 3 plus 2 plus 1. So now I have a total of 15 blocks. So this one went up 3, this one went up 4, this one went up 5. So for the 10th block, this is 5 blocks. 6 would go up by 6, so that'd be 21. 7 would go up by 7, so that'd be 28. 8 would go up by 8, be 36. 9 would go up by 9, which would be 45, and 10 blocks would go up by 10, so it'd be 55. And that was one possible way of explaining that picture there. And again, it's the same pattern that we had before. So that concludes the evens. Check the answers in the back of the book